Hi, well, had the night to sleep on it, and this morning I've finished off rearranging the breadboard, cleaning it up a little bit, and adding all of the components that we've been looking at, and tied it now into the high-powered MOSFET. I'm using a little bit of a crude current load for the power supply on the breadboard. I've got a bulb from an old 12-volt flashlight and a 10 ohm series resistor, so I haven't yet built a DC load device to actually properly test this, but between the waveform generator and the power transistor that I've got with the bulb and resistor in series, I can actually simulate around about a 1 or 2 amp transient load variation on the output of the power supply. So, you know, considering it's on a breadboard, it can give us a reasonable idea of how well it's performing. One of the other things I did once I was playing around with it this morning was I had a look at the transient response, and it wasn't as nice as I would like it to have been. Now, obviously, part of that is because it's on a breadboard, and part of it was because I had not yet put any bypass capacitors or anything like that. So I had a little bit of a play around, and came up with simply adding, I think, just two capacitors, 100 nanofarad, at two strategic points in the voltage control circuitry, and that pretty much completely eliminated the issues that I was having. So I will show you now exactly what that was and what was happening with it. It looked quite horrendous at the time, but it was all to do with the way that the integrators work and things like that. And the other thing that I found was that I had overestimated the resistor for the voltage integrator. I had 100K in there, and it should have been 100 ohms. So I just I mismarked it when I was drawing up the diagram. So I fixed that, and between the addition of the capacitors and changing that resistor to 100 ohms, I think that what I've got is quite respectable, considering it's all floating on a breadboard. So I've updated all my diagrams to reflect the current state of the design, and I'm going to provide these all on my post, and so that you can download the JPEGs or PDFs or whatever if you want, and use it yourself or modify it. So let's go and have a look at the board, and I'll show you on the oscilloscope what the output response is like on the output with the changing in current. So it'll give you a good idea of what the issues were and how they were solved. And then we'll have a quick look at the revised diagrams, and then a complete circuit that shows everything all put together. All right, so let's get right there. All right, so it still looks a little bit of a rat's nest on the board here, only because I'm using the TLE2144, sorry, the quad op amp that I was using before. I have another op amp here that's just acting as just a follower for the two pots for setting the volt and the current, because I don't have a DAC or any V reference set up at the moment. So it's just a little bit crude on the setting and the voltages, and rather than have it be non-linear because of the pot going into resistor summing nodes, I put the op amp there to give it a low impedance source to the summing junctions. We talked about that in the last video, so I won't go any further than that. Using the 50 milliohm load that we were using before, we've got the meters set up to monitor various points of the circuit, and we'll describe that as we go through. We have a common analog 0 down here, where all these resistors come across to one of the rails, and this white jumper lead goes across to the positive output of the MOSFET. Okay, now this is an important thing to remember. We're floating our analog circuit basically on the positive rail of the MOSFET just before the current sense resistor. And the reason for that is so that as our output goes up and down, so does our analog circuitry will follow it. It means you don't have to have your op amps working at plus 40 odd volts. You don't have to have high side drivers that have to work everything, to shift things from a 0 volt rail on the raw power up to in excess of 40 volts. You start having to get special op amps and things like that when you do that. And when we look at the circuit in a minute, you'll see exactly how that's been hooked in. It should be pretty clear. I've also upgraded the transformer that I was using. The one I had here before was only rated up to 1 amp, so it was starting to get warm, and as I was approaching 1 or slightly over 1 amp, the output voltage was actually dipping below 30 volts, and our design is actually to give us a 0 to 30 volt output. And the reason for that is the transformer that was currently mounted there before was a 12012, not a 15015. So the fact that we were getting a bit over 30 volts is just because we weren't loading it very much. So now the one I've put in here is a 4.5 amp 15015 transformer. So it's going to be easily able to supply the load we need. I'm not going to be able to load it up to 5 amps right now. For one, my power MOSFET is not on anywhere near big enough a heatsink to be dissipating low voltage outputs at high currents. I mean, I could probably set the output to say 30 volts or something at a high current, but then I don't have a DC load that can handle that either. That's one of the other projects I need to do so that I can actually do that. And I've got the parts already, I've just got to build it up. 15015 is our AC power coming in. That gives us about 46 volts on our capacitors here. Now, remember what I was saying about needing special op amps. If you were supplying your op amps from the 48 volts, you know, the actual regulated power from your main raw power supply, then these op amps would have to be working on 46 volts, and you'd want to have some headroom for safety reasons. So you're going to have to probably get things that can work on at least 50 to 60 volts. And that starts getting into specialized op amps. And what we want to do is have jelly bean parts if we can. And you know, the op amp that we're using here will quite happily work on plus or minus 15 up to about plus or minus 18. So what I'm doing right now is I'm just running it on plus or minus 12 volts, which is being supplied by a little switch mode power supply that's actually built into the base of this box right here that the breadboard's in. All right. So this thing has a built-in power supply underneath. Yeah, op amp. These two capacitors here that you can see sitting here right now, these are the two that I added into the circuit, and we'll describe that in a moment. What I want to do is I'll show you what the performance is like now of the transient response time when I change the loads, and you can see for yourself. It quite happily now will track from 0 to 30 volts because I've got plenty of high side volts to power this. I do not have any level shifters because our op amps are tracking the output of the MOSFET directly, so it's easy for them to control the MOSFET, because the actual MOSFET only requires about 2.5 volts to start turning on, and so you know, by the time you're actually turning it hard on, you're only about 4, 5, 6 volts between the gate and the source. So you know, at higher loads, obviously that has to drive higher. But it's easy for the op amp because it's got a whole 12 volts that it can do to keep control of it without having to do any special level shifting. Yeah, the current load down here, the DC load that I've got, all it is a power Darlington transistor. It's got a 1 ohm load that's actually sharing the same heatsink because I was doing some testing on a previous video. And what I've got over the side here is a bulb, 12 volt, and then I've got a 10 ohm resistor in series with it. This will quite easily take several amps if I wanted it to, but this being 10 ohms, you know, even at 1 amp, it's getting very, very hot already. So that's why it's important, I think, soon for me to build my DC load so that I can do some better testing. Anyway, I'm using my function generator to drive a transient response into the base, you know, into this power transistor, so that it can switch the current from, you know, maybe 100 milliamps up to about 1.5 amps. I'm going to set it up for about a, you know, between 1 and 5 hertz repetition rate so that we can get a nice signal on the oscilloscope. Down here I've just clipped a 1000 microfarad capacitor. It's a little bit big, but it's the only one I've got that fits right now onto the output rail, and I'm basically using the legs of it as the common clips. So like I said, it's a little bit kludgy because it's all breadboarded, so we are going to get some noise, we are going to get some offsets, and potentially a few current loops. I think the next stage is going to be to build this up on a proper piece of circuit board, and I may even end up designing a board for this as well now that I've got the schematics sorted out. So I think that's pretty much everything. Now I'm going to just power this up, and we'll see what it's going to do. Hopefully you can see everything there. Just making sure I'm not messing anything up here. I'm outputting a 200 millisecond 2 hertz signal. It's going from, it's sitting on 3.6 volts, and it's switching between it with a 2 volt peak to peak, so about 2.5 to 3.5 volts going into the power transistor. And as you can see, if I bring the over here, you can see the light is flashing on and off as the current's going up and down, just to give us a visual indication that things are working. These two meters are actually showing the volts that are coming onto the drive of the output of the summing integrators. So they're both sitting high at the moment, which is allowing the MOSFET to turn on, and these are not going to respond quick enough to be able to see what's really happening at the moment. So we will look at the oscilloscope to actually see what the signals are doing. Okay, so we have currently a 20 volt set point. The current is obviously fluctuating up and down as we're driving this right now. So remember, 50 millivolts on this meter here. So it's currently fluctuating between about 10 and 30. So that's probably about 100 milliamps to almost 300-400 milliamps. So we want to increase that a little bit. Things are currently quite cool, so that's probably why they're not doing much. So let me just increase the amplitude of the output of the pulse generator drive, although it is possible that I'm actually imposing a current limit too at the moment. Alright, so I've set the output to be 30 volts. The current is switching between, it's difficult to tell. I can't put the oscilloscope in more than one place at a time because obviously it's earth grounded, and if I put it in two different places, I run the risk of blowing something up. So right now I've got it up here monitoring the gate voltage, the drive voltage to the power transistor that's controlling the load onto the power supply, which is the yellow trace. All right, now what I'm giving it is, as I said, 200 millisecond increase in load twice a second, so it's running at 2 hertz, and I'm switching the drive voltage between it's peak to peak right now sitting at 2.7 volts, and it's set as an offset of 2.6, so it's going from about 1.5 volts up to sort of 5 and a bit volts. So it's definitely trying to maximize the output switching load. And what we're looking at on the blue trace up here on the oscilloscope is the transient response of the output. All right, so we're AC coupled so that I can just look at the response for this. If it's DC coupled, obviously it's 30 volts, it's sitting way high, and I won't be able to bring in enough offset to see this level of detail. And I've bandwidth limited. I can take that off, it won't make much difference. As you can see there, it's just a little bit of noise showing up, so I'll leave it off. So we're showing the transient response here for the output as we switch from a high load back to a low load, and then back up to a high load again. All right, these little spikes here, when the load comes off, the output is shooting up and then recovering. When the load comes back on again, the output is dipping and then recovering. And if we look at this with the oscilloscope, if I just capture that and actually zoom in, right, this is the current response. So it's 200 millivolts per division, so it's about 150 millivolt spike, and it's recovering within about 80 milliseconds. Now this is quite a high load, and it's this is something you wouldn't normally see, and this is also going from 0 to the load in about 500 microseconds. That's the edge I've put on the inputs. I don't think that'll particularly make much difference, but it's still switching it on very quickly. So if I now zoom into this, so that's a closer view now, and we've got, as I said, 200 millivolts per division. So it's dipping about 200 millivolts, just under, and it's taking 10-20 milliseconds, and it's back to normal for that shift. So that's not too bad, considering we're dealing with a 30 volt output load here. Dropping by 200 millivolts for a few milliseconds is not too bad at all. And as I said, this is all on a breadboard, so it's very difficult to actually control how well things are going to respond. If I look at the trailing edge of what is on, you can see here the load comes off, the output of the power supply jumps by about 200 millivolts, but then again it's recovered again within about 20 milliseconds, maybe about 15 milliseconds. It's back to normal. That is not too bad, considering, as I said, everything is sitting on a breadboard. If I actually now reduce the output voltage to say 10 volts or something, we can see if it's going to be any better. I'll change that to be actually triggering continuously. And we just change the output voltage here down to 10 volts. Now obviously this is not going to be able to get the same current output now, because it's got a fairly static load on it, but it's still pulsing that output. Now as you can see here now, the output transient response is way less, which is actually pretty good. So if I just up that to say 100 or 50 millivolts per division, so it's doing now, I've got 10 volts output and it's dipping at about 70 millivolts and recovering again within 10 mil. So that's pretty good. I can actually impose current limiting too. One of the things that that's all working as well with the integrators. So if I come down to the, well actually while I leave it there, I'll just start reducing the current limit. It's not going to work at the high end. We have to wait till we get to the low end, start pulling down the current. I'm going to increase the voltage to its max just so that we can have more current range to play with. This looks really bad. The reason it looks bad is because the current limiting is kicking in. So we're as the load comes on, the current limit is kicking in, recovering a little bit, and then the load's coming off and the current limit is releasing. So they're it's flipping between current limit and no current limit. And you can actually see this. Remember, we've got the summing junction on the meters. These two meters here are showing the output of the integrators, which feed through the diodes to pull down the gate of the MOSFET to turn it off. And as you can see, one of them is hooked up, this one is hooked up to the voltage side. I think this one is hooked up to the current side. And you can see it's flip-flopping between which one is driving and which one is relinquishing control. And that's because my current limit is lower than my voltage set point to get the actual load. So it's kicking in as my load's going up and down. If I increase the current limit again, back up right there, now it's stopped. You see this one is the voltage reading and it's now saying, hey, I don't care anymore, the current limiting has overloaded it. The voltage is actually technically trying to push the MOSFET harder on, so it's gone up to its top rail of 11.3 volts. It's a 12 volt supply, less a little bit in the op amp. So it's pushed as high as it can, and the current is now taking control. Now if I change the current limit by decreasing it, right, you can see the voltage is changing there a little bit. The output is still the same, but now I'm going to be able to drag the output down, right? That's back to where we were before. The voltage limit is still set to the max. So as I drag this down, the current limit is taking control. Now it's hard to tell what it's doing here because I'm switching the loads over such a range that it's actually coming in and out of control, which is a little bit difficult to see what's happening. If I actually put the output to a DC instead, like there, and I'll take that up to, well, take it up a little bit to increase the current. So now what we've got is you can see that the current is now pulling down the MOSFET, turning it off, because I've reduced the current down to 0, which means it's basically trying to turn the thing off. And if I zoom out a little bit so you can see all of the multimeters, this one here is showing us the actual output of the MOSFET, sorry, of the power supply. It's equivalent to what would be on the terminals of the front. This one is showing the current, so it's showing basically 0.25 millivolts, which means that's, you know, about 25 milliamps or something. It's not a lot at all, because I've set both of these to 0. Now if I start increasing the current, all right, you can see the voltage is being allowed to come up there. The voltage control is still sitting high because I've got it set to maximum, so its error is huge, but because of the diodes, it's not allowing it to drive the MOSFET back on. It's all in the hands of this one, which is connected to the current output of the integrator. As I increase the current, you can see the voltage there is increasing a little bit. Now this is sitting on the MOSFET, as I said, and you can see now that the current is sitting at 28 millivolts. So that would represent about a half an amp, just over. So as we increase this, all right, now we have about 1 amp set, and we've got about 14 volts on our output. So we're completely in control of the current at the moment. And as I increase this, I'm going to take it up to 1 amp. So 100 millivolts represents 2 amps. Sorry, I don't think I'll be able to get to 2 amps. 50 millivolts represents 1 amp. So we can get up to about 956. So it's just under 2 amps that's going through here. The resistor's getting very hot, burning my fingers. The bulb is nicely on, and the volts is now back up to 30 volts, which is where I set it. And you can see here, if I turn the current back down again, just by a little bit, right now the current is in control. The current is about, well, 1.5 amps-ish. The output of the current integrator is relatively low, 3 volts, which means it's pulling off the MOSFET to prevent it outputting too many volts. It's just slightly down, so it's sitting at 24, even though the set point is just over 30. And the output of the voltage integrator is sitting way high because it knows there's an error and it's basically ramped up to the positive rail. The minute I take this current, if I allow the current to go to max, the voltage one will actually then take over because it's sitting, the current, the way that the two are set up, it's going to flip because of the difference in the 2 op amps and the sensing and everything. So now you can see here that the current one has suddenly decided, oh, I'm not going to be able to get the current anymore because it's basically run out of headroom on the output voltage. And so it's gone high, saying I've got a lot of error. I want to be able to get more, but the diodes are preventing it. And now the diode and the differentiator integrator, the differential amplifier and integrator for the voltage side has basically now said, oh, I can control this again, and it's pulled its output down to maintain the output to 30 volts. And now if I take the voltage control pot and start cranking it down, you can see that I'm bringing the voltage down, and we're keeping in control still. So I can take this down to say 20 volts quite happily. All right, and I've got a 10-turn pot on here, so I can get it fairly accurate. And it's sitting there quite nicely. And yeah, so it's sitting in a nice static state. Things are probably going to be getting quite warm at the moment because I've got 46 volts on my power supply rails. I've got 20 volts here, and I've got just over an amp flowing, which means that I've got about 26 volts at an amp. So I'm dissipating about 26 to 30 watts in the heatsink of my MOSFET. And it's not a very big heatsink, and it's lying flat, so it's getting quite warm. So I'm not going to leave it there too long, but what I do want to do is have a look at the oscilloscope for a second again. Right now it's not triggering because we don't have a heavy load on it. Sorry, we don't have a changing load. So I'm going to set the triggering to be just free running for the moment, so we can have a look at what the ripple is like. So remember, channel 2 represents the output voltage. Channel 1 is the switch, which I've now set to DC. So I'm going to crank up it's AC coupled. So we're going to see if we can see what that's 50 millivolts, that's 110 millivolts per division. So you can see there's some noise. That noise is probably picking up from the switch mode power supply that's in my breadboard and all the other interference around here. Plus, this is all spaghetti hanging in the air, so I'm not surprised there's some noise there. I can probably put a filter on it. You've got full bandwidth, just take it down. That's reduced it somewhat to, for anything that's only less than 20 megahertz. So that's pretty good. It's a fairly smooth output, and that's at 20 volts. If I bring it down to 10 volts, it's AC, so just give it a second to recover. That's just about 10 volts. So you can see it's still quite good. Go down to 1 volt. So that's 1 volt on the output. The noise is not increasing or anything like that, which is quite nice. All right, so let's just crank this back up to the full 30 volts, and we'll put it in current limiting and see what the output looks like for a static state. All right, so that's just under 2 amps that's flowing through it right now. So that's maximum voltage and about 2 amps of the output because I don't have a good enough load at the moment to go any higher. So now let's just start cranking down the current. And again, it's going to, I'm going to take it down to 1 amp. All right, that's set to 1 amp now for the current. So there's a little bit of noise there. I don't think it's really any more than what there was before. It's undulating a little bit, probably because of the noise of the board, and the integrator is probably going up and down a little bit, trying to stabilize it or keep it in a constant position. And of course, the things are starting to heat up, so I'm getting temperature drifts and things. So it's probably continually trying to compensate. It's just going to take it down to so that the output is sitting at about 5 volts. That's got a 5 volt output using current limiting. So that's actually 18 millivolts, so that's 50 is a 1 amp, so it's about 200 and 300 milliamps or thereabouts on the output current, and that's still behaving nicely. Let's just take it down to almost, that's turned off now. Both of them are cranked down to 0. And so that noise is consistent across there, but I can tell you if I put this onto the supply rails, you're going to see the same amount of noise. So now let's put the the signal generator back on. So that's having some effect because obviously the DC load now is switching off and back on and off and back on. So it's, and remember we're at 10 millivolts here, so this is only 30-40 millivolts of noise. So let's just crank this down a little bit. Right, so it's set to 200 millivolts per division. I'm going to crank the current up and we'll allow it to be controlled by the voltage. Well, the meter's reading an average of 75, so it's probably going up to at least 100, which would indicate about 2 amps, which bears, which basically is what I would expect it to be. So we've got 30 volts pulsing between probably about half an amp or less and 2 amps, and we're getting this 100 millivolt spike up and down as we're switching. Now what I want to do, I'm going to change the triggering back to where it was. So what I want to do now is I'm going to change the waveform. What I'm going to do is, first of all, I'll increase the load width to say 800 milliseconds. No, 400 milliseconds, because I'm doing it. All right, so you can see there it's made no difference whatsoever to the transient response at all, even though I'm now have loading it for a longer period of time. It's only a 500 millisecond total transition time, so I'm actually only releasing the load for a small amount. Now if I go the other way and make it say 100 milliseconds pulse width, all right, so it's just the same. Now let's just make it down to say 10 milliseconds. So it's a very narrow pulse. You can see now that it's actually having a slightly less effect on it, probably because the capacitors and things are having a better chance to compensate for the transient response than what they were having before with the bigger load being applied to them. It's quite narrow. It's actually not showing up. I've just put it up to 5 milliseconds. Let me just expand. All right, sorry about the arm getting in the way there. So now you can see here we've got the transient, the pulse of 5 milliseconds right now, and it's having very little effect on this. It's 200 millivolts, so let's just crank that up to 50 millivolts, 100, go down one, 10 millivolts. That's 20 millivolts per division. So with that pulse of 5 milliseconds taking the current, you can see it's having very little effect, and it's actually recovering within 20 milliseconds, so much faster recovery time for that narrower pulse. So I'm actually quite happy with that, considering it's all on a breadboard. So I don't know, what I'm going to do now is I'm going to just try and put a different signal in. I'm going to flip this from being a pulse to being a nice smooth sine wave, which, this is a brutal way of testing it by putting in a square wave. So if I put in a pulse like this, if I put in a nice sine wave with the same parameters, now I'm giving it a 2 hertz sine wave where I'm changing the load from virtually nothing up to the 2 amps. And you can see here that, reduce my, gotta let that trigger, there we go. So we've got, with a sine wave, you can see there's still a little bit of a transition as it goes through between no load and as the load comes up. But it's actually dealing with it quite well. And even with, if I go square wave, all right, now we've got the sharp edges. We're getting these higher spikes on the leading and trailing edge where it's compensating, but it's still 20, 40, 60 millivolts, probably 100 millivolts with the extra bit that you probably can't see on the scope. So that, considering that's a square wave, like a post-load step change, it's dealing with it quite well. That's a triangle wave I'm feeding into it now, and you can see it's actually back to a little bit of a better response time. The measured signal on the transistor, of course, is not showing it to be very linear because of the nature of the transistor and things. It's varying its load as the voltage is ramping up on it. But it's still got, you know, about a plus or minus 20 millivolt pulse, 20-30 millivolts as it's going through that load. If I change the actual amplitude now of the of what I'm driving here, let's make it just a 1 volt. So that's a much smaller transition, and I'll change the offset, bring it down a little bit. So now we've got a more realistic variance on the load. We've still got 30 volts out. Things are still getting very warm over here. But you can see now that the output is only varying about 10 millivolts with that, which is quite good. Just reduce the bandwidth down there a little bit. Sorry, the time base. So you can see it's still having a little bit of effect as it's transitioning, but it's only about less than 10 millivolts of variation on the output with this. And even if I now go to a pulse with the same parameters, right, we've got these spikes again that are coming in, but they're only about 20-30 millivolts now in either direction. They're very small, and they're recovering very quickly. If I increase the time base again, sorry, arm's getting in the way too. All right, so we're at 10 milliseconds. So we're back to recovering within a few milliseconds of a step change of a pulse, but with, you know, with more realistic waveforms like a ramp or you know, sine wave kind of loads, the power supply is quite happily keeping up with it. So anyway, that's the power supply and its operation. Now what I want to quickly show you now is I'm going to remove the 2 capacitors that I put in there for handling the transient responses, and show you what effect it has. So in order to do that, I'm going to put a square wave back in, and I'm going to increase the amplitude of my signal back to 2.5 volts. So we're going to be hammering this thing again. I'm going to reduce that down. Okay, so there's the signal with pretty much switching between almost no load and 2 amps. 2 times a second with a 50% duty cycle. And you can see the spikes here are still recovering fairly quickly, but they are, you know, getting excessive. Like it's about 200 millivolts shoot up and down as we hit the transitions. Now if I take the capacitor that I put on the feed that goes in from the summing junction to the integrator, all right, what I did was I put a 100 nanofarad capacitor out of the voltage differential amplifier, basically across the 132K that feeds to the integrator. So if I pull that out right now, it's out now. And of course, sod's law, it doesn't show any difference. The other one, let me just pull out the other one as well, because that should now make quite a difference. Right? So what you have here now is you've got this ringing occurring. See, it's difficult to tell. You can see now the integrator is jumping up and down. This is with low load, and you can see the sawtooth effect of the integrator. Right? And then when we've got maximum load, it's still doing it all the way along, and it's not settling down, and the spikes are actually much bigger on here. So putting in these capacitors, the 0.1s, I'm going to try and gingerly put it back in on the live system here without blowing anything up. Just trying to find the right places to put them. Yeah, that's the one on the integrator. And as you can see, it's cut down the noise considerably. And then the other one I put in was across the 100K going to the positive input of the voltage differential amplifier. So that one might be a little harder to put in. Managed to get them back in without blowing anything up. So we're back to basically having this 100 odd millivolt spike. So as I said, it's on a breadboard, and you can see just with those two capacitors, it's made quite a difference. So if I now show you what I've done with this on the diagrams, like I said, I'm going to make these diagrams available to everybody. So let's just go down and have a look. So what we have here on the diagram is I've added on the V negative rail, the V sense minus, I've added a 100 nanofarad, a 0.1 microfarad capacitor across the 100K sense resistor. And then on the output of the amplifier that goes to the difference summing junction, I've put another 100 nanofarad across the output 132K resistor here. And what this is basically doing is it's allowing the response to change based on the sharper edges coming out, and it's dampening the oscillations. So here it's reducing the gain because you're no longer 100K and 22K. You're basically, for a sharp edge, you're pretty much a short circuit for a very short period of time. So it's not going to react anywhere near as quickly by having this in here, and it's going to dampen down any oscillations, which is exactly what we've seen. And then by having one here, we allow it to respond a little bit quicker to the changes by bypassing this just for a fraction while this charges up. So it's not going to be there, have much of an effect, but again, it dampens down a little bit of the ringing and things. So that's what I've changed there. On the current sensing, I haven't changed anything. This is exactly as it was before. I've cleaned the diagram up and provided some color coordination. And as I said, I'll provide these diagrams as well. The integrator now, one of the changes that I did here, which I mentioned to you before, is that I had a 100K here on the voltage integrator, and it should have been 100 ohms, so I've changed that to be 100 ohms now, and that's improved the response time of the integrator as well. Obviously, 100K here, it's a lot slower to integrate than having 100 ohms. So this has made it much more responsive. The current one has not changed. I've also put the same 4.7 nanofarad because I was actually going a little bit high on both, so I've just reduced these down to a more realistic value, and it seems to be behaving quite well. If I do design a PCB for this, what I'll do is I'll make room for varying the components quite a bit by having extra pads for parallel and serialing resistors and things. And then let's have a look on the power stage. Now I showed you this before, and what I've done is this really hasn't changed, but what I've done is I've added some extra layout on here to just help understand exactly how things are going to get configured. So what we have here is you've got the raw input that's coming in from your rectified 15/015 and smoothed power. So this, I've called this V raw plus, comes into our MOSFET driver stage. We then have VREG, which is this small orange track, before we hit the current sense resistor. Now, if you keep these very close together, basically you can mount the 50 ohm current sense resistor right on the heatsink along with the power MOSFET. And then we've got the V out, which is going to go to your front terminals of your power supply. So what what I've added to this, and what I'm going to do is I'm going to build up a little board that basically sits right there with the heatsink, with the MOSFET and current sense, which provides all these little connections to go to the control circuitry. I've got 3 diodes. I've got a V gate, which is our 12 to 15 volt supply coming in to drive the MOSFET high, with a 6 volt and a 10K Zener. If you go up to more towards 15 volts here, you might want to change the Zener to be about 9 volts. And then we just got a 10K in series with the gate just to reduce a little bit of ringing on the MOSFET. And then we have 3 basically jelly bean diodes that are being allowing us to sum the control. So whichever one is pulling lowest takes control. So we've got a voltage control input, a current control input, and a question mark control input. Now this one could be used for a power good. So maybe you got a V reference or something like that, and a little bit of a comparator on the output of your VREF or one of your your digital control power supply to detect that it's good and now in control, feeding into here would prevent the output from spiking or anything before the control system is ready to do anything. We've got a analog 0 volt, so your analog supply, which is your plus or minus 12 to plus or minus 15, you need to reference it. Remember, I wanted saying that we want to reference it to the positive output of the MOSFET, so that all floats on top of there. So there's the point where you connect, and you can see I'm connecting it right up here on the output of the MOSFET. All right. The current sense plus and minus go against the either side of the 50 ohm current sense resistor. I'm going to use a 4-terminal one here. If you don't have a 4-terminal one, you can use an axial with, if you've got the wires on an axial resistor, what you can do is solder 2 wires for your main current on the outer parts of the wire of the resistor, and then solder 2 additional sense wires directly onto the wires of the sense resistor as well, slightly closer to the body of the resistor, and that would give you as close as you can get to a 4-terminal resistor without actually having to spend the extra money to get one. I'm fortunate enough that Vishay sent me a few to play with to use in my experiments and things, so I'm going to be using a full 4-terminal current sense resistor, 50 milliohms. Now, we're working on the assumption that we're going to have a 5 amp power supply. So 50 milliohms is going to give us 250 millivolts at the 5 amps. And all of the resistors and everything else in the current control is based on expecting 250 millivolts differential across the current sense resistor. If you change this to be 100 milliohms or something else, then you will have to recalculate the resistors to compensate for that. We have a V-sense plus and a V-sense minus, and these two connections are actually, they're supposed to go straight to the terminal that is the output of the power supply. You could also add an extra terminal for V-sense and have an external shorting between them if you wanted to remote the sense, but in our first iteration we're just going to have it tapped to the same terminal. These don't have to be heavy wires because all they are is voltage sensing, so they're actually a high impedance input. And as you've seen already on the other circuit, there's actually a 100K resistor between the V-sense and the inputs of the op-amp, so it's at least 100K on the V out for the V sensing, and it's not going to have any impact on the load or anything like that. And then the V minus is going straight to the common ground of the raw power supply. Again, it's connecting at the terminal going out of the power supply, not at the smoothing capacitors. If you put it at the wrong end or the wrong position, it won't be giving you the correct voltage, especially on high currents, because you could drop easily 100 millivolts or more across the tracks of either across a cable or across the tracks of a PCB at high currents. If you in that situation, you don't want to have that offsetting your voltage sense. And that pretty much is everything on the power stage. I'm using an IRFP 064 from Vishay. This is capable of very high current, very high power. It's a very fast switching. It's designed for use in switch mode power supplies and everything else, but it also is an ideal N-channel MOSFET to use here. It performs very, very well. And then finally, what I've put together is a complete diagram which has all of the pieces plugged in, and I've color-coded it to match the colors that I've used on the other diagram, so that it makes it easy to follow the individual pieces. So we've got the current sensing, we've got the voltage sensing, we've got the voltage and current integrators, we've got the power stage, which is basically this bit in the middle with the current sense resistor, the MOSFET, the diodes for controlling it, and our little input to give the biasing to the MOSFET to power it on. And we've got our extra diode for something like power good or whatever else you might want to use it for. You can add more diodes here too, by the way. You're not restricted to just having 3. If you've got something else, like you want to set a high current threshold or some kind of emergency shutdown or anything like that, you can also quite easily just add the extra ones, add it to the control circuitry, and it'll be able to control the MOSFET as well. I think that's pretty much it. So yeah, one of the things you can do with this output too, although I'm not sure whether you'd want to do it this way, is even with a microcontroller, if you wanted to turn the output off, you can just have a diode feeding into here, and then in the logic input of the microcontroller through a level shifter could then drive this thing quite happily. Yeah, so you can add a level shifter from the output of a microcontroller or something like that, and you're going to be able to drive an additional input to here to basically switch the output off if you want to through remote control. You wouldn't have to necessarily go to a switch or adjust the settings on the front panel or anything. You could do it quite easily remotely. Other things you might want to add to this could be a crowbar on the output in the event of a detected problem. Having the ability to inject a sine wave or something like that, or some kind of control signal that allows you to introduce noise and things. So if you want to do some testing, you could also basically do here, if you crank up the current and the voltage and then you have this extra input point, you could very easily do that. But you could also do that, of course, by driving the current set point or the voltage set point too from a DAC, especially if you've got a DAC. You could do that. If you're using a potentiometer for those 2 points, then you could easily add an extra input either to the summing junction or to the input to the power stage through a diode with a separate little op amp and everything, and allow yourself to inject a arbitrary waveform generator or something, so that you can actually create step load, step output, and things like that to allow extra testing capability. Anyway, I think that's pretty much it. I hope you enjoyed that. It's been quite long in doing, and been quite interesting playing around with how these things are going to behave. But the next step now for the power supply, of course, is to put this onto a real board. I will, as I say, provide all the diagrams that I've finally come up with, and we'll move on to adding computer-based control to this. So I think I will build this up on a piece of Veriboard or something, so that it's going to be more stable and a lot less loose wires, less risk of frying something. And once we have it on the Veriboard, we can start adding the microcontroller. In the previous videos, that if you look on my YouTube channel, you will see that I've already started working on a Raspberry Pi based control panel with Windows 10 on it, and driving digital to analog, analog to digital converters, as well as relays and things. So that would be an ideal control solution for this. Now obviously, if you want to have multi-channel power supply output and also have DC load and various other things as well, then you would need to use isolators, and I've already shown how they can be used on my Raspberry Pi video for Windows 10 and other ones, where I'm using an I2C isolator that provides up to about 4,000 volts of isolation on the I2C bus from the system that you're controlling, from the actual microcontroller that's the master of the I2C. And I've also, you've also got these available for SPI bus as well. So I'm going to be using those. What I will do is, I think, also put together my DC load, because I'm starting to feel the pinch of not having one, and I think it would be very beneficial for me to have it, so that I can do some more formal testing of the power supply. But that's about it. I've run out of things to say on this current iteration, so we will leave it at that. And as I say, if you like, then click the like or the plus thumbs up as appropriate, and I hope you'll be back for more when I release the next video. Please provide feedback, and if you want to see me test other features, then let me know, and I'll see what I can do.